All right, this note slide video is going to be talking about position time and velocity time graphs. Again, a very abstract concept, and we are going to attempt to put them to more concrete images of graphs. So we do have questions for consideration in the upcoming notes, and those are these three things. I want to know what a position time graph is. You need to know what a velocity time graph is. And you need to know how the features of one graph translate into the features of the other. So they are related. So we're going to start off with position time graphs, or also called distance time graphs. These are going to show the position as a function of time. That is the function that you cover in math class. So there is going to be a big chunk of math coming your way. But yes, position as a function of time. So we are going to have two axes. Our x-axis, which is going to have time on it, and our y-axis, which is going to have distance on it. Now, it is very important that when you draw these graphs, you label your axis, because the distance time graph and the velocity time graph are going to be very similar looking, but the biggest difference, the way you're going to tell the difference between the two, are those axes. So make sure for distance time, we have distance on the y, time on the x. Time is independent, y is dependent. Distance is dependent on how much time you travel. All right, so first we're going to imagine a ball rolling around on a table. Here we have an illustration of it. We're flashing a strobe light, if you can imagine that, at every second, so we don't actually see the ball move, we just see it at different positions. So if we're flashing it at every second and the ball is going 1 inch per second here, or sorry, these are actually centimeters, 1 centimeter per second here, we're going to start plotting this as a function of time on a graph. So if you think about it, at 0 seconds, my distance is 0. At 1 second, my distance is 1 centimeter. At 2 seconds, my distance is 2 centimeters. At 3 seconds, my distance is 3 centimeters. All the way up till I stopped at 10 seconds, my distance is 10 centimeters. So here we are with our graph. We have our axes. I have time on my x-axis. It is in the units of seconds. I have distance on my y-axis. It is in the units of centimeters. And I'm going to start plotting my point. My first one was at 1 second. It goes at a time of 1 second and 1 distance. 2 seconds, 2 distance. 3 seconds, 3 distance. 4, 5, 6, 7, 8, 9, and 10. You'll note I plotted all those points as a function of time now. And now I'm going to estimate the time between them by connecting them with a line. You will note that it goes through 0, 0, because at 0 seconds I had a distance of 0. And now we have our first distance time graph. Moving that over here. Let's look at it. What are some of the characteristics of this graph? Well, I know I have a straight line that has a upward slope, or a positive slope to it. It is increasing, going from left to right. So we call that a positive slope. You will note that slope is the steepness of the line, so it is a constant steepness. That's not changing in that. And therefore, I can say that its speed is a constant speed. I do not know direction here, so I can't really say velocity. I just know that this is going at a constant speed because it has a constant slope. Right, there you go, constant speed. Each type of motion has a characteristic shape on our graph. So we have a constant speed, we have 0 speed, that would be like at rest, or we have accelerating, which is speeding up, or we have decelerating, again, a negative acceleration, which would be slowing down. Constant speed is going to be represented by straight line segments. So here we go, boom, that's a straight line. That is constant speed. Note how my slope does not change. Yeah, it has some negative distance here. That just means I'm getting, I started off over here to my reference point, got closer to my reference point, then got further away from my reference point in a different direction. So I do get a little direction here, but there's not a lot of context for direction in these. Over here, I have a constant speed in a negative direction, so I'm starting away from my object, getting closer to it, and then going past it as it goes. Again, this line here on my y-axis would be 0 in distance, so I'm getting closer to whatever my reference point is, and then I'm going in the opposite direction away from it. So I do have a negative direction in that case. When I have a flat horizontal line, note that slope is 0 here. I still have a constant slope, so it is going at a constant speed. However, my constant speed is 0. My position is not changing as time goes. If you could imagine there being a 2 here, this would be a distance of 2 as time goes on. It's not going up, it's not going down. It is a constant speed because my slope is constant. It is a speed of 0 because I am not changing position. It's my flat line here is going to be an object at rest. It is not moving. Curve segments also up here. This is a change in speed. Here you can see how slope is getting steeper and steeper as time goes on. Again, slope is your speed in this case. So if my slope is getting steeper, then I am speeding up. This is going in a positive direction. Well, eventually it's getting closer to you, and then it's passing you and going in your positive direction, whatever that might mean to your context. And over here is going in a negative direction. So you really, again, you don't get a lot with the direction on here, but you can see a little bit of it. Here we're traveling in a positive direction, but as you can see, our slope is actually decreasing, our steepness of our line. Again, slope is steepness of the line. The steepness of the line here is decreasing. So therefore, this is traveling in a positive direction, but it's slowing down. Over here is traveling in a negative direction. Again, our slope is getting kind of flatter as time goes on. So we are getting, if you can, let's just keep me up here. You are seeing that I am going in a negative direction here, but I am slowing down as well because my slope is getting less steep. The slope of the distance time graph, again, is going to be equal to its velocity. You don't get a lot with the direction here, but you can get some based on whether it crosses this axis and is getting further away from it or closer to it. But here we have positive slope, constant slope, and therefore it is going to be moving away from us at a constant speed, or a constant velocity, because I can tell you it's moving away from us, whatever direction that may be. There's still a little there. You can see here's my equations for it. I can calculate slope, which is the steepness of this line. Slope is change in y over change in x, or you could use delta y over delta x. Again, this should be covered in math class more, but I'm assuming this is mostly a review. If it is not, please ask questions on how to do this more in depth. But here we can see our change in y. What is our final change in y? Our final time is 30. Our first time is, I guess I'm down here at time, we should do change in y is position. Sorry about that. Let's start with position. Our first position is at 10 and our final position is at 30. So final position, again, just like velocity, final is first, initial is last. And time goes from 0 to 30, so that's a total time of 30, or 30 minus 0. And we get 30 minus 10 gives you the 20, 30 minus 0 gives you the 30, so that's 2/3, or 20 divided by 30 meters per second, which will give you your adjusted for sig figs speed, and that is again going to be equal to your slope. Slope is also rise over run. So rise, it went up once, twice, but they're in things of 10, so it goes up 2. Hey, look at that. Run, it goes over 3. Hey, look at that. 2/3 would also be equivalent to 0.67 meters per second. Following this distance time graph, we can see that it corresponds with an object moving back and forth along a straight path. As we go from our first segment here, we have a constant slope, so we have a constant speed going away from us. Eventually it's going to turn into a changing slope, which means we have a change in our speed, or an acceleration here actually. And it is going to actually be slowing down. You can see our slope is getting less and less and less until it's eventually coming to a horizontal line, which is no motion at all. So here our object stops, and then it is going to come back towards us at a fairly constant speed because the slope is not changing. It is going to pass us, start moving away from us again, and then it is going to come to an extremely quick stop. It is just going to abruptly stop for some strange reason. It is honestly physically impossible to do that, but for our purposes, the time-wise here, it's just going to stop moving right away. Physically speaking, you have to slow down before you stop. Time or speed is continuous measurement. You cannot go from 30 to 0. You have to go from 30 to 29 to 28 and so on down to 0. So you do have to slow down eventually. Then it will stop again, and it will start to accelerate back towards us, because again, our position would be at 0, and move on from there. Our next slideshow will pick up here at velocity time graphs.